speaker is Justin, and he will be on the academic job market this year. So if you're hiring, please contact and talk to Justin offline. The talk will be about how to debug proof search.
Thank you. We all know how frustrating it can be to have a buggy proof or program, but at least we have techniques like type systems or debuggers to help us systematically figure out exactly where something went awry. In contrast, when what we're trying to debug is a search procedure that is looking for a proof or a program, we don't have such luck. There's no proof or program to step through in the first place. This has been one of the hardest problems with proof search for decades. Today, I'd like to share with you a new approach for debugging failing proof search based on a general framework that you can apply particular strategies to a given setting. So let's dive into the details. Proof search is ubiquitous and powerful, powering things like database query engines like Datalog, many program synthesizers, type systems like the trait system in Rust or type classes in Haskell, and of course, tactics and interactive theorem provers like ESOP for Lean. And proof search, when it works, is amazing. But what happens when proof search fails? Well, in Datalog, if we ask for a fact that doesn't exist, we might get something like check failed. Or in program synthesis, if we try to synthesize a program for a specification that's unsatisfiable, we might get back something that just says not possible. Now, the Rust community has put in a lot of effort into making really good error messages, but there's only so much that a static error message can do. In this case, I have one missing trait implementation, and that window is showing the error messages that I'm getting. In fact, this is actually just only 3 out of the 11 different errors that I get for a missing trait implementation. Similarly, for ESOP for Lean, when it fails to prove a particular proposition, you can ask it to show you the trace of things that it tried. But for this one missing lemma, this window that I show you right here is the trace that it's going to give you. And in fact, if you can see the scroll bar, that's actually just a tiny % of the trace. So what makes it so hard to explain what went wrong with proof search? Well, to see why, we can represent proof search using this data structure called an and/or graph and understand exactly why it's so hard. So an and/or graph is a data structure that's a bipartite graph consisting of or nodes and and nodes, where or nodes, we'll say, are going to be provable if any of their children succeed. We'll say that an and node is going to succeed if all of its children are going to be provable. In practice, though, the and/or graphs that we're going to be looking at are not so neat and tidy. Here's one that I extracted from a Rust trait error using the Argus tool that Gray et al. Introduced at PLDI here last year. And you can see that it's much bigger. And here's one that I extracted from a proof search from ESOP in Lean. Now, I don't know about you, but I think that these graphs make for beautiful art. But the prospect of trying to figure out what actions I need to take as a user in order to fix this situation fills me with a sort of existential horror. It's just too big and unknowable to know exactly what we need to do. But this is nothing new. Researchers have been talking about the difficulties of debugging these and/or graphs for decades, dating back to at least 1991, all the way up to more modern times. I like the way that Sene and Lazzari put it in 1991, which is as true now as it was then, which is that even though a proof tree, which you can think of as just the and part of an and/or graph, gives a brief account of the solution steps performed during the computation, it only does so for the goals that have been solved in the process. However, it presents neither the goals that have been tried but unsolved, nor the alternative clauses that could have been used to find an alternative solution. A bit more graphically, you can think of as an and graph as a buggy program or proof. And the tools that we have to help us here are things like type systems or step-based debuggers or algorithmic debugging. Whereas an and/or graph is more like all possible failing programs and proofs. And the main tools that we have to help us here are visualizing those graphs that I was showing you on the previous slides, or some sort of graph traversal. Maybe we start at the top and do some sort of top-down exploration, or some sort of bottom-up exploration from the leaves. But in practice, we saw that these graphs are very, very large, and it's very hard to know what to do, what actionable steps to take as a user. So what are we to do? Well, I want to point out that these and/or graphs are not just graphs. We'll start from the observation that hidden inside these and/or graphs are mini proof systems that can be poked and prodded, and we can ask hypothetical questions about. So for example, for this tiny and/or graph right here, we have this tiny proof system, and we can say, what would happen if the user were to prove B or C or D? For example, maybe one modification we make is to axiomatize B and C, corresponding to the user manually proving B and C, and we can find out what will happen in that situation. Or maybe we make this modification right here that axiomatizes C and D. So our key insight is that we don't want to display or traverse this and/or graph. Instead, what we want to do is we want to navigate the space of modifications to the graph and help the user arrive at one that's going to prove the goal. OK, so let me show you what a concrete example of this would look like when we're debugging ESOP proof search for lean. The modifications that we're going to allow for the user are labeling or assuming possible lemmas. And our goal is going to be derived from a program. The program is going to be derived from a program that's in the test suite for Limperg's and Fromm's ESOP proof search tool. And it's going to be about a big step, operational semantics. And we're going to be proving specifically something about the if-then-else construct, although the details don't matter too much. OK, now, instead of looking at this graph to understand why ESOP cannot prove this proposition, what we're going to do is we're going to have the system help the user navigate possible modifications to this graph. OK, so first thing that's going to happen is the system is going to select a proposition, perhaps this one right here. This proposition is going to differ from the first one in that it's just going to be the forward part of the by implication. Now, for a moment, put aside how the system is going to select this proposition. We're going to return to that later in the talk, so we'll just take that for granted for right now. But now, interestingly, what the user is going to be able to do is they're going to respond with some labels about this proposition. So they'll be able to say that they're willing to prove this proposition manually, that they're not willing to prove it manually, but this proposition should be true, or that they're willing to prove it manually and that this proposition must be used in the final proof of the goal, or similarly, that they're not willing to prove it manually, but that it should be true and it must be used, or they can just say, I don't know. Now, crucially, what we're going to require the system not to show is should be false, because there's no way for this proposition to be false while the first goal is still going to be true. So if the user were to select that label, then their specification would become unsatisfiable. And this is a property that we're going to call in a moment strong soundness. OK, so let's say that the user is not willing to prove this manually. Not sure if it's quite showing up, but let's say they're not willing to prove it manually, but it should be true. Then maybe the system is going to select a new proposition, and the user is going to respond with a new set of labels. In this case, all of the above options are going to be OK to show. And now the user can also select that this proposition should be false, because there are ways to prove those top two propositions while this bottom one is still false or unproven. OK, this turns out to be a critical lemma about the big step operational semantics. And so maybe the user is willing to prove this manually. And the interactive session can end there. But how do we actually achieve this interactive specification refinement process with the kinds of guarantees that we want, where the user is not going to be able to go down one of these rabbit holes of like an invalid label? Well, I've been working on a technique called programming navigation that can be used for exactly these sorts of situations where we need to do some kind of interactive specification refinement process. And we've applied it to synthesizing bioinformatics analyses from wet lab experimental workflows, for creating user schedules for a sparse tensor algebra compiler. But today, I want to talk about how this can be done for debugging failing proof search. OK, but to do that, I need to tell you a little bit about what programming by navigation is. So the idea with programming by navigation is that we're going to model a space of possible expressions or programs, as well as the steps between the programs that you can use to get to each other. In this particular context of debugging failing proof search, these programs are going to be proof system modifications. So maybe this one in the center is just the identity modification that does nothing. Maybe this one is the one that axiomatizes proposition X, and maybe this one is the one that axiomatizes proposition Y. The green stars are going to be the valid solutions, which in this context are going to correspond to proof system modifications that are actually going to prove the final goal. So maybe this one right here that's very close to that one in the center is going to be the trivial modification that simply axiomatizes the goal. Unfortunately, that would be a bit of a rude suggestion to show to the user, because if the user is asking a proof search tool to prove something and it fails to prove it and it says, hey, how about you prove it instead, that's maybe not exactly what the user would want to experience. Instead, maybe what they would want is a modification that's a little bit further out. So this is maybe the desired modification that's going to prove the goal. OK, so the way the programming by navigation is going to work is we're going to start in the center here. And if we just imagine a sort of traditional program editing experience, you'd basically be able to get to any of these nodes however you want. But let's take a look at this step right here. If the user were to take that step, then they would enter a part of the program space where there's no way to get back on track to some valid solution. So if we think about what kind of support we would want from a programming system, we would actually want to require that this step not be shown. Instead, we want to show steps like sigma A right here, which are en route to some valid solution. Generalizing a bit, we also don't want to show those two steps right there. And this is the property that I mentioned before of strong soundness, which is that only valid steps are shown. Of course, that's only half the battle. We also want to be able to guarantee that the user can navigate to any of those green stars. For example, if they want to get to 3, 4, or 5, they need to be able to take those two steps right there. And this is a property that we'll call strong completeness, which is that the shown steps are going to be comprehensive enough to be able for the user to reach any of the valid solutions. Then the user can select one of the steps, update the current working expression with that step, and repeat the process as necessary. So at a high level, the way that programming by navigation is going to work is we're going to have a step provider that is going to be providing sets of steps that the step decider, i.e. the user, can select between. And we're guaranteeing that any of those options are going to eventually be en route to some valid solution. So maybe they select this particular label, and the process will continue. OK, so how do we implement a programming by navigation system? Well, there's three main ingredients. First, you need some notion of expressions, you need a notion of validity on those expressions, and then you also need to decide what the steps are and how you're going to be showing them to the user. So we can go through each of these different main ingredients for each of the different cases that I was talking about before, but let's just do it for debugging failing proof search. We've decided that our notion of expression is going to be these proof system modifications, and we've also decided that our notion of validity is that the modification is going to need to prove the final goal. That just leaves how we're going to be providing these steps to the user. OK. Before I talk about what the step providers are, there's one last helpful building block, which is this idea of a non-empty completion oracle. We'll say that the completion of an expression is going to be the set of valid expressions that are reachable from it. So if we take a look at this schematic from earlier, the completion of the expression in the middle is going to be all 5 green stars, and the completion of that expression is just going to be the stars 1 and 2. It turns out that for this particular domain where we're talking about these proof system modifications, we can actually define a procedure phi that is going to compile an expression down to a SAT formula, and we'll maintain the property that phi applied to some expression is going to be satisfiable if and only if the completion of that expression is non-empty. And we have the details in about 1 page in the appendix to our paper, so if you're curious about them, you can take a look at it there. The key takeaway is, though, that we can really quickly check whether or not this completion is going to be non-empty, and that's going to turn out to be super useful to be able to define these step providers with very little amount of code. OK, so first I want to give a sort of warm-up step provider that's going to replicate an existing strategy that we're all going to be familiar with to traverse these trees, which is a top-down step provider. So I just want to show you that we're not losing anything by having all this programming by navigation. In a moment, we'll see novel strategies that are sort of non-topological. OK, the way that it's going to work is we're going to maintain a frontier of labeled propositions, and then we're going to loop over all rules that are going to have a conclusion in that frontier. In this case, there's only one rule. Then we're going to select or collect the set of premises to that particular rule, and we're going to show the user we're going to let the user select which set of propositions they want to label next. So maybe in this case, there's only one option, so the user makes that particular selection, and we're going to repeat the process. Now there's actually 3 rules that have a conclusion in the frontier. And so there's going to be 3 sets of premises for the user to select between to label. And so maybe they perform another selection, and they've chosen this one right here. And you can see that by going through this process of selecting which of the sets of premises they want to label next, they are essentially doing a top-down traversal of the and/or graph. But if that's all we could do, then there'd really not be a point for introducing all of this programming by navigation stuff. And so now let's talk about some non-topological step providers that don't follow the edges and nodes directly of the graph. And the simplest one that we can start with is this idea of a random step provider. So like the name suggests, a random step provider is just going to choose a random proposition and to select to show to the user. Then for that particular proposition, it's going to loop through all possible labels for that proposition. And using that non-empty completion oracle that we talked about a moment ago, it's going to check which of those resulting labels is going to result in an expression that has a non-empty completion. And then it's going to show that to the user to select between. So even though the propositions are going to be randomly selected, the labels are still going to be filtered. So we're actually still going to be able to satisfy our strong soundness. Now, I'm not going to stand up here and say that random is the best step provider ever, because as a user, it would probably be quite overwhelming to just be like bombarded with a bunch of random propositions to label. And so to motivate our next step provider, yes, sorry. So the user can select and this process can repeat. But to motivate our next step provider, I want to go back to that large angular graph from Aesop and Lean just a moment ago and zoom in a little bit to right here. So it turns out that this particular proposition right here is actually very special. And there's essentially no way that you could know this just by looking at this visualization. But by special, I mean that if it's assumed, then the goal is going to be proven, and most valid labels for this particular proposition actually happen to axiomatize that proposition. So all else being equal, if we were to show this proposition to the user, there's a very high probability that the interactive session would actually end right there and we'd be done. And so perhaps this is a proposition that we would want to show to the user. Using that non-empty completion oracle that I mentioned a few slides ago, it's actually really easy to essentially compute a score for each of the different propositions that's going to be capturing this idea of how close we're going to be to ending the interactive session. And so we can just apply that score to each of the propositions, and then instead of randomly selecting a proposition, we can actually just take the argmin of the scores of those propositions and show that one to the user. So just by subbing out essentially one line of code, we can get a totally different user experience with our step provider. And that's, instead of random, that's what we call our cut step provider. And that's actually the step provider that we used to have that 2-round interactive session earlier in the talk. Those were the propositions that were selected with this strategy. OK, so we saw our notion of expressions and validity and a couple step providers. In the paper, we define a bunch more step providers. For example, one's based on information theory, when you use like expected information gain about like asking the user about certain propositions. We also have some based on sort of traditional why not provenance from the database theory literature, and so on. All of these are going to be super easy to define using this non-empty completion oracle that we just need to define once up front, which for this particular setting we defined via compilation to sat. So with that, I'd like to thank my collaborators, Marlena, Max, and Sarah, and I'm more than happy to take any questions. Thank you.
Go ahead.
Hey, Adam Japala from MIT. The and/or structure seems very propositional, and I'm trying to figure out what this means for first-order logic and beyond. Probably relatively easy to handle for all that below the bar of what you're trying to prove, but exists below the bar. How does that manifest?
Yeah, absolutely. I think that's totally an open question. So for right now, I think that you even start to run into this even with ESOP, where you might have like different existentials that it needs to like insert to like complete the proof search. And we don't really have a good answer of like what that would look like, but if we can define a suitable data structure that's going to be encapsulating those sorts of quantifiers, then perhaps we may also be able to define like suitable modifications to that data structure. Yeah, it's a great question.
Thanks.
Thanks.
More questions from the audience? I have a question for you. So I imagine different step providers will be good for different workload, right? Like, do you have, I don't know if you have run those kind of experiments, but do you have some insights on like what kind of step provider will be good for, what kind of workflow? For example, if I'm doing like Rust trait error debugging, or I'm doing a theorem proving using tactics, and maybe I should use top-down approach in this scenario, and so on.
Yeah, that is a great question. Thank you. So I think that like I was finding, I don't have any like empirical results to say like exactly like one is better than the other, but just like in using it, I think that the cut step provider turned out to be like quite useful for these sorts of things, and for lean. And then for for the Rust trait errors, it turns out that like all of these step providers that I was mentioning are actually compositional. Like you can kind of like combine any of them with each other, and you'll still satisfy all of the properties. And so something like cut or maybe max information gain to get like to a certain part of the tree for a Rust trait error, and then using maybe a bottom-up and top-down step provider to sort of like explore the traits around that one seems like it could be a sort of promising strategy. But yeah, I think that it's going to super depend on the domain. Thanks. It's a great question.
Cool. Thank you. All right, let's thank the speaker again.